Hello everyone, my name is Min-Kyu Lee and I'm excited to present our research on AESOP Auto-Encoded Supervision for Perceptual Image Super Resolution, which was recently accepted at CVPR 2025. This work is in collaboration between Sang-Hee Kyun, Woo-Jin Jun, and my advisor, Professor Jae-Pil Ho. Now let's begin by answering the question, what is super resolution? Super resolution, or simply SR, is a technique in computer vision that aims to enhance the resolution of a low resolution image. Let's go through a simple example of how super resolution works. First, we start with a low resolution input image on the left side. As you can see, it appears blurry and lacks detail. Next, we apply an AI-based super resolution model represented by the small AI robot in the center. This model has been trained on large datasets of low resolution and high resolution image pairs, allowing it to estimate and restore missing details of the low resolution image. Finally, we'll get a high resolution output on the right side, which is much sharper with clear textures and more fine details. We understand the concept of super resolution. Let's take a look at some visual examples of our method applied to times 4 upscaling. On this slide, you see several side-by-side comparisons of low-resolution input images and their corresponding high-resolution outputs generated using our proposed super-resolution model. Each example demonstrates how our model effectively restores fine details, enhances textures, and improves overall sharpness compared to the blurry low-resolution input. One of the biggest issues in super resolution is that it's an outpost problem, which means that we can't determine a unique solution. Since the AI model doesn't know which version is the ground truth image, it often generates a result that averages among all possible solutions, which tends to be blurry. Notably, this happens for any per pixel loss. And throughout this presentation, I will use the term LPix to represent any per pixel L1 or L2 loss and other variants of them. Jumping deeper into details, this diagram provides graphical illustration of the overall super resolution system and highlights one of its key challenges. First, let's discuss the role of LPix, the pixel-wise loss function. LPix is essentially a form of maximum likelihood estimation, simply MLE, which means it optimizes the probability distribution over the prediction space to find the point that maximizes the expected likelihood. However, this optimization process does not select a single plausible HR solution. Instead, it converges to an average result, which is why the final output often becomes blurry. This is one of the fundamental problems in traditional super resolution approaches. And then the question is, how can we move away from these blurry results and instead train models that generate sharp and perceptually convincing images? For now, the common solution to the blurring phenomenon is to introduce perceptual loss, LVGG, and the adversarial loss, LGAN, to enhance realism and fine details. I won't go into much details about these loss functions, but what you need to remember is that these additional losses significantly improve visual quality and are widely used in modern super resolution models, but often hinder fidelity convergence. Important point here is this a free lunch? Can we get sharper and more realistic images without any drawbacks? The answer is unfortunately no here. And in fact, there is a fundamental theoretical limitation to super resolution models, which we call the perception distortion trade-off. Let's dive deeper into what perception distortion trade-off is. Let's first look at the left side of the slide, which provides a conceptual illustration of this problem. The yellow and gray circles represent different possible high-resolution images that could correspond to a given low-resolution input. The blue dot labeled as fidelity SR image represents an output optimized for minimum per pixel error. And this approach produces blurry images because it's the average among all possible solutions, which we have discussed earlier. The pink dot labeled as perceptual SR image represents an SR result optimized for realism using additional perceptual oriented losses. And this version introduces much more natural textures and high-frequency details, but has additional error highlighted by the red arrow, because the generated high-frequency textures are different from the actual high-resolution image, which must lead to lower fidelity scores. Now let's look at the perception distortion trade-off curve on the right side. This curve shows the fundamental relationship between perception, which indicates realism, and distortion, which indicates per pixel error in super resolution models. We have a blue curve here, which indicates the upper bound of an ideal super resolution model. And as you can see, we have a clear trade-off relationship where when we aim for improved perception, we must lose fidelity and vice versa. Theoretically, no method cannot go under this curve. And when we say that a model performs better than the other, we mean that it's closer to the blue curve. In this work, we're also aiming to go closer to this blue curve, not going across this line. Now, given the concept of the perception distortion trade-off, we'll discuss if prior approaches are optimal. They either multiply a small coefficient to LPICs or apply low-pass filters before them. This design is to reduce the impact of high-frequency components from being penalized, which is a fundamental cause of the blurring phenomena. However, later I'll show that these certain conventions both lose more reconstruction guidance than required. That means they lead to higher distortion than required for their given perceptual level, as shown in the graph on the right side. From now on, I'll introduce you our method and some concept we have defined for this. Here, we first define the term fidelity bias and the perceptual variance. The perceptual variance is the random factor when we perform image super resolution and leads to blur when removed. The fidelity bias is the average solution of the super resolution process, or else the fidelity SR version of an SR image. Accordingly, we could define the ground truth fidelity bias, which is the optimal fidelity point, and the fidelity bias induced error, which is the distance between our predicted fidelity bias and the optimal fidelity point. Looking at the left side of the diagram, we see that perceptual super-resolution images contain a range of plausible high-resolution outputs. This variance represents natural texture differences that should not be eliminated and has some inherent randomness. If we over-optimize for fidelity and remove this perceptual variance, our model will collapse into a single average prediction leading to blurry results, the very problem we wanted to avoid. Now, given a certain level of perceptual quality, we should aim to minimize the fidelity bias-induced error to improve fidelity. In other words, we want to simply align the blue and gray circles. Importantly, minimizing this error does not affect perceptual variance. It only provides improved fidelity without harming realism. This means that we can reduce per pixel error while maintaining perceptual quality if we only minimize fidelity bias-induced error. From now on, we'll refer to this perceptual variance induced error as the variance effect VE and the fidelity bias induced error, which is the systematic effect, as SE. Overall, we're claiming that we must preserve VE while minimize SE. Thus, we'll show that current approaches are failing to do this, and we will accordingly propose a method to achieve preserving VE and minimizing SE.
Here, I don't want to go into the details about complicated math, but note that LPICS is basically MLE as in the upper right corner, and this can be divided into two terms, which is exactly the terms we have defined in the previous slide, the SE term and the VE term. This means that LPICS can be understood as minimizing both SE and VE. Since we have discussed that VE reduction leads to blur, we have now narrowed down which factor of LPICS specifically leads to blur. So visually, the overall optimization procedure would look like this. The prediction space, the blue circle, will be aligned towards the true solution space, a gray circle. But also, it will degenerate to the sole average point, leading to blurry results. Accordingly, we can think about a straightforward solution, which I will introduce you in the next slide. Instead of minimizing both SE and VE, we could design loss function where only SE is minimized. By doing this, we could improve fidelity scores for a given level of perception level without leading to additional blur for this guidance. Visually, instead of both aligning and degenerating the prediction space, we propose only to align the centroids of each space, as in the right side of the figure. This would be a simple overview of our method, where we replace LPIX, the per pixel L1 loss or L2 loss, fundamentally reducing both SE and VE, into a loss function that only reduces SE, the systematic effect. Then we apply this with other perceptual quality-oriented losses together, which will now lead to the highest perceptual quality the perceptual losses can provide, while achieving the highest fidelity scores for that specific given level of perception. So what would be nice if you could compare these left and right figures, and about the SE plus VE, which indicates LPIX, and only SE, which stands for our proposed loss function. Now that we understand the importance of separating fidelity biases and perceptual variance, the next question would be, how can we estimate the fidelity bias of a given image? Since fidelity bias is the systematic deviation that causes error in traditional SR models, we need a way to quantify this and somehow minimize it. To achieve this, we introduce a differentiable operator psi, which acts as a fidelity bias estimator. The role of psi is to take an image as input and estimate its fidelity bias. Instead of using the conventional LPIX loss, which we know leads to blurring due to pixel-wise averaging, we propose a new approach. We use the fidelity bias estimator psi to compute a new loss function, which directly measures and minimizes SE. By training our SR model to reduce the systematic error rather than per pixel differences, we can maintain sharp perceptual details, improve fidelity without sacrificing perceptual quality, and also avoid the blurring effect of traditional pixel-wise losses. This means that our method effectively substitutes LPIX with a loss function that directly targets fidelity biases, leading to a better balance between realism and accuracy. Now, overall, finally, our method can be summarized as first pre-training an autoencoder as in the left side of this slide, and then substituting the original LPIX with the proposed autoencoded loss. This enables us to only reduce SE while preserve VE, which was impossible under conventional per pixel reconstruction loss, indicated as LPIX. Now, when we put everything together with other loss functions, we get the following figure. This slide compares the impact of traditional loss functions versus our proposed approach when using perceptual super resolution tasks. The key difference here lies in how fidelity bias and perceptual variance are handled. In the baseline method, both fidelity bias-induced error and perceptual variances are reduced. Thus, the prediction spaces are aligned, but are also degenerated, leading to blurry results. Meanwhile, in the proposed method, the fidelity bias is aligned with the one from the ground truth space, while perceptual variance is preserved. Additionally, an important point here is that we do not apply a small scaling factor for the reconstruction loss. This type of small lambda for the reconstruction loss was to reduce the impact of VE reduction, thereby avoid blurring. However, this also reduces unintentionally the SE reduction factor. This means that the network cannot receive sufficient reconstruction guidance, and since the adversarial loss works in a task-blind manner, it generates realistic textures but are not guaranteed to adhere to the input image. Accordingly, the adversarial loss with reduced SE reduction will potentially lead the super resolution network to generate images that does not precisely align with the input image, or also may lead to unintended visual artifacts. Meanwhile, since we do not multiply a small coefficient, we can get a much more stronger reconstruction guidance while also avoid blurring. Here, we provide some intuitive figures that compares our proposed AESOP loss against conventional per pixel level loss. As can be seen, since we have isolated SE and VE and only penalized based on SE, the loss scale exhibited by our proposed loss is smaller compared to the original LPIX loss. However, when the coefficients are applied, our loss shows significantly higher level of scale, indicating that we provide much stronger reconstruction guidance as discussed in the prior slides. Below, we also have some visual examples of the loss maps of each losses. And LPIX blindly penalizes all factors of the image, even including the very high frequency details that cannot be regressed by super resolution models and what lead to blurring if penalized. Accordingly, this leads to obvious blurring as shown in B of this figure. Meanwhile, the proposed AESOP loss only tackles the factor that can be regressed, and these do not include the very high frequency details with randomness that would lead to blur if reduced, but does include the overall structure of the image, which acts as an important reconstruction guidance and does not induce blur. Accordingly, we can generate images that both adhere better to the original LR image and also has significant improvement in the visual quality. Here we compare the performance of a super resolution model trained with hour loss and the conventional per pixel LPIX loss. AE-PSNR and LR-PSNR are each PSNR scores after the autoencoder and after downsampling. AE-PSNR directly indicates the level of fidelity bias induced error, or simply SE, and higher AE-PSNR indicates that we have well aligned the prediction space and the solution space. Meanwhile, LR-PSNR indicates how well our image adheres to the original input image, and we show significant improvement in both metrics. We believe that this is due to the significantly stronger level of reconstruction guidance we have provided, since we do not multiply a small coefficient to the reconstruction loss factor. Here we have the overall benchmark table comparing prior state-of-the-art method with both the RRDB backbone, which is a CNN-based super resolution architecture, and a SWIN-IR backbone, which is a SWIN transform-based architecture. As can be seen, we achieved state-of-the-art performance in all datasets over all metrics. I won't go into details about each baseline methods or evaluation metrics here. You just have to know that despite perceptual quality metrics and distortion metrics are often known to have trade-off relationships, and it is often very hard to improve both of them. By simply introducing a pre-trained autoencoder enables this significant performance improvement. In the prior slide, I've shown that our method leads to improvement in both perceptual metrics and also in distortion metrics. Now we'll show them in a graph. I recapped that earlier slides where I have introduced about the perception distortion trade-off curve. We say that a method performs better if it's closer to the left bottom corner. And as can be seen, we significantly outperform baseline methods, including the most recent state-of-the-art method, LDL. We also have more visualization for the perception distortion trade-off curve and comparison with other recent baselines in the supplementary materials. So we highly suggest you to have a look for them. I won't go into details for that since we have limited time here. We finally will show some visual results here. Since we do not reduce VE, we can see significantly improved perceptual quality, for example, in the fine-grained hair textures. Also, since we do not multiply small coefficient to the reconstruction loss term, we provide a much more stronger reconstruction guidance overall. Thus, we can generate images with much more or less visual artifacts that are induced by adversarial training. I'd like to thank you all for your time and attention today. I hope this talk has given you a clear understanding of super resolution, the perception distortion trade-off, and how our method addresses these challenges. If you're interested in more details and have any questions, feel free to check out our paper or reach out to me via the email address below. Thank you.